provide me with some feedback concerning whether this looks fine.
Okay.
So just a moment, please. So sharing this one. So how does it look?
It looks fine. We can see you, we can hear you, and the slides are visible. Thank you.
Okay, if there are any problems, just let me know via the mic. So, because
Will
I
do.
won't be able to check the
Sure.
the
Will do.
screen. So actually, this is an approach based on computational intelligence to support smart cities, focusing on air quality. So the quest for better life, according to Aristotle, was the reasoning behind the establishment of cities. People organized cities to find safety and happiness, and he said, to lead a good life. And although there has been 2,500 years from then, people still accumulate to cities, and we all know what's going to happen because we have seen this happening in the last decades. That's one fact. The other fact is that we have um, uh, very many new big cities that are formulating themselves in the last years. And more than 90% of the overall population growth being attributed to cities in the 21st century. This means that the majority of global emissions, air pollution emissions, will come and already comes from cities, the majority of energy use. And so we know that there are specific pressures in terms of population growth. This has an impact on air pollution also. Traffic congestion, one of the main mechanisms for worsening air quality, as we have seen very well in the previous presentation, where the amazing work that has been done in Bradford has been, I think, a unique example of how people can deal with that. Insufficient space in terms of housing, public open spaces, and green spaces. The requirement for resource management in terms of energy and water, for example, or climate change, or economic pressures and infrastructure sprawl. This overall means that there is a deterioration in quality of life within the urban environment. And actually, when it comes to air pollution, this is an old problem being present in this new era, in this new world. So we know how air quality influences health, and not only humans, but we can also already include, we know how to include, let's say, all the environment in the equation, so to speak. An interesting notion having to do with what's the key situation in Europe currently. And in this slide that I have borrowed from a recent study, it's clear that if we adopt, as this is the tendency now, that's the suggestion in the update of the EU directive on air quality. If we adopt the recent guidelines, the updated guidelines of the World Health Organization, the majority of the European population will live in unhealthy conditions concerning particles and also most of the gaseous pollutants. So these are some facts. We know them. Some other facts have to do with the way that we are informed as citizens concerning air quality, air pollution levels. And this type of information comes from satellite, from models, any type of models, deterministic, statistical, data-driven. These are estimations of reality based on mathematics and knowledge of the physics, chemistry, etc. of the environment. Of course, reference instrumentation, and in our first presentation today, we had the chance to have a very clear view of which are the stakes when we are using instrumentation, either reference ones or low cost, for example, sensors, which is an emerging population of instruments and devices becoming more and more popular as they become more and more accessible to more and more people in various parts of the world. We can even try with considerable success to extract information concerning air quality levels from social media. They can be, let's say, considered soft sensors. And there are other sources of information. In all cases, this information is generated by instruments, by computations, by humans, and is provided via various communication channels, electronic channels, the internet, websites, social media, etc., mobile apps, any other type of electronic media, or even other non-conventional, if you like, media. We have had successful artistic installations trying to depict and, let's say, translate in a different, new, fresh way information concerning the quality of the breathed air. Now, in this landscape, the current, let's say, state of the art has to do with a combination of various scientific fields, tools, and approaches. And this is one of the things that we try to do in a project that is being running in Thessaloniki. We call it Custom, where the idea is that, first of all, we are going to monitor. Monitor is being done already with the aid of a number of reference instruments, reference monitoring stations to be more precise, operating in the area, 7 of them, according to the EU standards and directive guidelines. Then what we are doing is that we are employing state-of-the-art meteorological and atmospheric dispersion and chemistry and diffusion modeling, fueled with information coming from satellite data in order to have more detailed emissions, fueled with information coming from other modeling infrastructures and services like Copernicus, so that at the end we have a nice set of information concerning the estimation of air quality levels in the graded area. We want to complement this information not only with official monitoring data, but also with data coming from low-cost sensors that have been deployed in the field, and to use machine learning and artificial intelligence in order to treat those sensor data. So I can describe later on, and even at the end of today's presentations during the discussion session, how calibration can be done in low-cost sensors. So we use this for this to cover this need, as well as for fusing information. And concerning citizen, let's say, centered information provision currently, what's the case in most of European cities is something like that. So there is an official website allowing citizens to receive information concerning the hourly variation of regulated pollutants in various places in the city. And the other, let's say, official source of information in Europe, at least, is the Copernicus atmospheric quality information bouquet of services. So this means that, at least in Europe, wherever you go, you find one or more official, let's say, air quality monitoring stations in medium to large size cities for European standards, I mean. And Europe is also covered by a modeling infrastructure that is funded, powered, updated by European institutions. Coming to the use of low-cost sensors, that's a completely different story. As it has already been said, we need to have additional information that depicts the spatial and temporal resolution of human activities. So that's something that is of high importance because this is where exposure happens. But we cannot reflect upon those local conditions unless we have a more dense network of information provision in space and in time. So one of the things that we have been doing in Thessaloniki is to test, as it was said in the first presentation, low-cost sensors or affordable cost sensor devices, putting them side by side to get to know how they behave, when monitoring various pollutants and how they compare to each other. And this information helped us also set up this network of 33 IoT oriented air quality monitoring nodes in the city in the frame of the custom project, making use of LoRa as a communication method. And this is the map of the nodes where the different colors denote that some nodes have only particles plus meteorological conditions, and some other nodes have particles, meteor, nitrogen dioxide, ozone, and carbon monoxide in addition. And the effort was done so as to cover mostly the densely populated city center, urban center, but also cover areas surrounding the most dense part of the urban web. Now, one thing that I will not go into detail a lot because I believe that it won't be very useful at this point is, as it has already been said, what happens due to the fact that low-cost sensor devices, like these ones, do not behave as reference instruments. They have drifts, they have shifts, and they don't live forever. There was this question, and maybe we can discuss it at the end, but definitely for different pollutants, there is a different aging factor. And what I can tell you is that in an environment, in a demanding environment for a sensor to operate, demanding, why? Because in the winter in Thessaloniki, we can have low temperatures around zero sometimes, low for Greek standards, I mean, with high humidity, while in the summer, we can have dry conditions with very high temperatures. So because this type of sensor nodes are usually equipped concerning gaseous pollutants with electrochemical sensors, those sensors demonstrate fatigue. So they get tired. And this fatigue can appear even if they are less than 1 year old. So this means that you need to change those sensor elements within these sensor boxes regularly. This means that you have a new device that needs to be recalibrated. While concerning particles, the lifespan of particle optical counters, because this is the technology that has been used in this type of low-cost sensor devices, allows them to live more, but nevertheless, they still suffer. And if they operate in demanding conditions, and we had an example of such a device operating in the seaside at the island of Crete, you know, this big island in the southern part of Eastern Mediterranean, then it got damaged due to sea spray and sea salt quite differently, and it was corrupted actually. All the metal components and the composites were corrupted. So this means that at the end of the day, you need to have a calibration procedure. And what we have been applying is a machine learning based calibration procedure. This means, if you like, I can ask and I can respond to questions, but the overall idea is that the initial signals go through a data analytics process where the final features, the final set of attributes that are being used, all those coming from low-cost sensors, are fixed. Then we have a variety of ways to pick up the most important of those features, most important in terms of the information burden they carry, so how valuable they are in terms of the information they can bring into this calculation. We employ some machine learning algorithms, not just one, but a number of those in order to have the advantage of ensemble learning. We stack them with the aid of a genetic algorithm. This practically means that we combine them, allowing an optimization to be run for how to combine them. So the optimum combination of this type of calculations is being handled by a genetic algorithm so as to have the final result. And what's the result? It's a better measurement. What I show here is in three areas. Of course, names should not tell you anything unless you have visited the city quite often. So this is, let's say, city center and some industrial area and some inhabited area. And these are PM10. And this is the relative expanded uncertainty. I know that this is an issue that we are going to discuss at the end, but there was, I think, a question on how to judge the accuracy of low-cost sensors and how to guide citizens. So actually, for the first time in December 2021, there was an ISO standard that came out of the work of a working group with lots of specialists working in the field. And this ISO standard specifically mentions which criteria should be used in order to categorize the different sensor either nodes or elements when they operate in the field. So this categorization has to do with a specific parameter, the relative expanded uncertainty. And this for high quality measurements for PM10, when they are compared to a reference measurements, should be less than 25% or less than 50% for indicative measurements, as they are called in the Air Quality Framework Directive. So what this strange figure tells us? That initially, this is how my sensor behaves. I would like this sensor to be below this threshold. And this is what I can achieve in various locations where I employ different computational procedures. So for a considerable window of concentration values, for concentrations from 20 up to approximately 100 micrograms per cubic meter, the sensor behaves, the sensor that initially was a low cost, low accuracy, high drift, etc. sensor can be corrected so as to behave as if this was a higher accuracy instrument. So this is what we call as a machine learning powered computational improvement of low cost sensors. But also, what else can one use in order to have better information that will arrive at the end at the doorstep at the hands of citizens as well as decision makers? Data sources include these improved sensor nodes that I mentioned, first of all, so that we have much better information from their operation on the field. Also, we have this nicely modeled up to 72 hours ahead forecast of air quality levels, but in a scale of not 2 square kilometers, sorry, it's 4 square kilometers. It's 2 times 2 kilometers. So with a grid size, with an area, a square area of a size of 2 times 2 kilometers. So not very accurate in terms of resolution in space. We need to improve this. We also have local climate zones, and this is important information for air pollution. Why? Because different local climate zones usually have a different influence in local air quality. And this is information that one can derive, and this is what we did in Thessaloniki, with the aid of satellite images, making use of a specific methodology. It's called the WINDAP methodology. It's very important to have city operation data, and maybe the most pronounced, most important, or among the most important sets of information of this type are traffic data. For Thessaloniki and for many other cities, there are some live data being available, and this was really one of the most, if the not, if the ultimately, if not the most important set of information that we could use, because we have traffic volume information at the street level. We also have meteorology from complementary measurements, so not only official, but also unofficial meteorological measurements done by citizens with the aid of privately owned instruments. And this is another role of citizen science, where citizen science can complement and support this type of activities by providing data. And we use data fusion for the rescue, as we say here. So to combine all this and come up with a much finer, in terms of spatial scale, a resolution of information, and in terms of temporal scale, in order to, as we say, to bring the information to where citizens live and commute at the street level, at the neighborhood level. But this is all outdoors, and as it was very nicely underlined by the previous presentation, we seem to forget the importance of indoors. So one of the things that we are working on currently is how to join, let's say, how to treat in a similar way, or not to stop, let's say, taking care of what's the air pollution when the door closes. So we wanted to open the door, and we used a school building in the city center to do such a study. So to take into account the information from the fine scale information produced so far that I hope that I explained, plus measurements that are being done within the classroom, again with low-cost instruments, and we can discuss this in detail. I think that it deserves some of our, let's say, attention here. These are findings of one specific day. It's in the kindergarten of this school. So what we have here is the number of people in the classroom, how the classroom starts to operate. These signs suggest either gaming activity in groups or learning activity in groups. This is learning by gaming. This is learning in groups for elementary, for kindergarten children. And the red line depicts carbon dioxide levels. The light blue line depicts PM 2.5 levels, both being estimated by a low-cost instrument that we provided for them. One of the reasons that they wanted to, and they were very enthusiastic, and actually they suggested scenarios. So they were very engaged, and they were engaged because they knew the problems. One of the reasons was the COVID protocol for schools in Greece, dictating that schools should operate even during winter with the door open or some window open. So they were worried about the temperature in the room, about the ventilation, the refreshing ratio of the air, you name it. And they had some rooms where they had mechanical cleaning of the air, some others without mechanical cleaning of the air, and they wanted to see the impact of all these. So which are the next steps to improve the intelligence behind the data fusion, to simultaneously, as I said, address indoor air quality seamlessly, outdoor plus indoor, wherever people are, whatever they do, to personalize in a pervasive, adaptable way the air quality information provision, to take into account the citizen science and the benefit of citizen science generated data, and maybe address soft sensor data in terms of posts in Twitter and other social media. Also to extend to biological weather, which is not, let's say, traditional air pollution, but just allow me to say that there are, let's say, aeroallergens like pollen in various places in Europe that have a great effect in people's quality of life, and they are airborne. So just two of the core guys being behind this endeavor. And I had the chance, speaking among the last people, to hear what you have said and just to complement on the previous presentation with a couple of slides. So this is something completely different. We did something similar with citizens that made measurements indoors. This is in Greek. I didn't have the chance to translate it. So what it reads here is that this is PM10, the orange, and PM2.5 in the living room where the door is open, and in the nearby kitchen, somebody is frying things. And this is where frying was recorded in the handwritten diary of activities that we used. And concerning also how citizen science can have contribute to the understanding, the same person using driving his car within the main traffic flow, and then when this person saw that these are the concentration levels I monitor in my cabin, changing to alternative routes. So just a small comment from my side. Collaborations with various institutes in this way, and okay. Last info, I will post it now. I will upload the file. We are organizing also a workshop on innovative systems for air quality monitoring and forecasting. You are all mostly welcomed on the 23rd of November, early for GMT time, from 7 o'clock in the morning, because it's 9 o'clock in Greece, to 11:30, it's 1:30 in Greece. Hybrid. I will post the agenda. You are mostly welcomed. And another comment, you might know that there is a relevant working group of the European Citizen Science Association working on air quality. It's open for everybody to join, to register, join, and take part in the meetings. Many thanks for your patience.
Thank you so much, Kostas, for your presentation. Please do post those two links, the working group link and also the event